Good afternoon. Before I start, any questions? So, if you haven't checked Piazza, I sent out instructions on uh, submitting the project proposal. So, remember there are two steps to it. One is that sort of the step one by Wednesday, end of the day, sort of fill out based upon discussions with me and all what project you're doing, and there's a set of questions sort of that I ask. And then you'll create a shell of a GitHub repository. So I'm using this GitHub feature called GitHub Classroom, and the way it works is that um, you sign up there. It will offer you uh, a class roster, and you're going to select yourself within that, and you're going to give your team a name. I would suggest just your project title, and then it will create a repository, and then you'll have to enter that repository URL in the uh, Google form that I circulated, so as part of the link to which I circulated. Only one member per team should do it, and you should fill out this form only after you have had discussion with me and have met the mentors so that the project is kind of finalized. Then after you have done this, by Monday, I would like you to flesh out that GitHub repository. I had a suggested sort of structure there, but the main thing is that in GitHub, every repository can have a project page attached to it. You go under settings and kind of create that page. So that's your main page, and you can think of that as a continually evolving project report. But you should have sections in them by Monday on kind of work out a weekly level um, sort of timeline as to how you plan to approach this thing. I'll send out another link to a shared spreadsheet where I would like you to put components that you need. Now, for you to do that, not everything needs to be purchased because a lot of you are doing projects for which either the parts I already have in the lab or I have substantively equivalent parts. So in the Google form, I've asked you to list things that sort of you expect to have. The way it works is I'm going to take that spreadsheet and have my assistant place the order. I would like you to stick to major vendors so that we can have clustering. So usually we tend to order from places like Amazon, Newegg, Mouser, DigiKey, and Seed Studio, SparkFun, and Adafruit. So they're kind of the major ones, but try to cluster them if possible. Sort of give us options. Make sure the part is in stock. Otherwise, it's going to cause needless delay. And so in the shared spreadsheet, what you should do is to sort of leave a few rows and then kind of make the entry for your team, okay? And don't trash or overwrite what others have previously entered. I'm going to put in the columns that I expect you to have, but they'll basically the URL, vendor, part, price, stuff like that. But again, anything significant that you need, quite likely I already have it. But you should do this stuff the sooner you can, so that because some of the things do take a week or so at least to arrive. So try to get it there, and again, kind of discuss that with me. I'll take a look at the Google Forms as sort of they start getting filled also. Anything I expect that so there'll be no so things like laptops and all you should already have, but embedded computers that they are fair game, so Raspberry Pi or those kind of things. Passive components you probably won't know at this stage, and for some of the stuff I might just tell you to purchase, keep the receipt, and we reimburse you at the very end. But you should do that only after I have approved it, okay, not on your own. So again, over the next week, basically, then, so you fill out, create GitHub accounts if you don't have one, fill out the Google form, set up your GitHub repository / corresponding project page, fill out the components or parts or whatever you need into the spreadsheet. Think about the timeline, and again, very important to talk with your mentor or me just to make sure that the plan is worked out. Yeah, so actually someone contacted me, so I'm going to be meeting, I forget you, right, yeah, 5:15 I told you, so if you want, you can come after him. I don't know, how long will it take for us? Half an hour? Half an hour, so 5:45. Okay. Any other questions? Okay. And
For the proposal, do we have to like follow any specific format?
The Google form kind of asks for all that information, and some of it you can then use that, like I'm asking for things like what's the objective, stuff like that. How very important, you should know very well that what's the endpoint there you are trying to achieve, assuming you're successful, and also how will you evaluate. The form forces you to think about it, and then that would be at least starting fodder for your kind of like online report. Okay. And then when the time comes later on, any slides you might create for, and you will have to create for the final presentation, any demo video, stuff like that. Just these repositories for now are set to be private, and anyone who you have administrative privileges on it. I did that just because I didn't know whether you have to manually add collaborators or not. You set it up, right?
Yes.
And so does it ask you all your team members in one go up front? No.
The first admin puts in first, and then he has to add the other.
And he has to add others. Okay. Yeah, I wasn't sure of that, how the team one worked. Okay, so after things are settled, I'm going to remove the admin privileges because I don't want you to delete the repository at some point in time. Okay, so but for now you have admin privileges, and so yeah, just set things up. I have obviously naturally access to all the repositories as well. If you don't know how to use GitHub, it's a good opportunity to learn. It is a very useful tool. The language it uses for the web page and all is something called Markdown. It's kind of very simplified. Instead of HTML and all, you kind of write in this. You can have heading, insert diagrams, stuff like that. So it's reasonably nice to get a good project page up and running. At some stage, I would also like to make this public. Right now, I'm not doing it simply because some of the project ideas are things that are relatively early stage and they may be publishable, so I don't want to kind of preempt that. Do not put anything which is someone else's intellectual property there, so you don't want to be caught in a situation where we are distributing something else. You can put links to them. Okay, so those were the things there.
So for the project page, is it going to be a markdown like the README, something for that particular?
You can create linked pages and stuff like that. At that point, you can have multiple markdowns. You can. I'll check, but yeah, I don't know whether there's a way to also put HTML stuff and link to that. Anyone knows? You can. Okay. So up to you. Which way you kind of structure that. And if you just Google for GitHub pages, or then it takes you to the website where it kind of describes the whole structure there. Again, those of you who haven't used JIT, you would need to install JIT on your local computer. There's also a very nice GUI type setup, which I tend to use, so you can just copy back and forth the repositories and coordinate with your partner, so to say. Any other questions? How many of you have never used JIT or GitHub rather? Okay, so just a handful. If you need help, come and talk with me, but good to know that most of you have. Okay, any other questions before? Oh, one other thing. So next Monday, let me make sure. Yeah, I think next Monday there's no lecture and I'll have to do a makeup. Unfortunately, everyone who could do a makeup from my group, I wanted to have an Android lecture. They're also going to exactly the same meeting. So we will not have a lecture and I'll make up for it either through an online video or set up something in an evening and record it. I usually have a student kind of give a lecture on Android architecture and kind of walk through that. But again, like I said, the two obvious candidates I have, Mustafa and Po, who some of you have met, they're both going to be at the same meeting. Okay, so continuing with the platform thing, so we looked at processor, we looked at communication interfaces, we looked at power subsystems. Next up is sensing, and I guess because embedded systems interact with the physical world, sensing is almost always present. You may have embedded systems which don't act back on the physical world in the sense that they may go on to provide information for policy making and things like that, but sensing is almost always there, and vast majority of IoT devices currently are nothing but really sensors. So there are two types of sensors you will find in embedded systems very broadly. There are sensors whose purpose is to measure the state of the external world. So in essence, sensing is fundamentally about not the data you're capturing, but after you have processed it, it's a problem of state estimation. That and either deciding what the current state is, or predicting a future state, or just tracking the trajectory of the state. And by state, what I mean is some set of variables about the physical world, and that includes humans and all, which are of interest for your decision making. So that doesn't necessarily include everything about the thing, but just the relevant knowledge which you need for the decision making. But the second set of sensors, which are also equally prevalent, is sensors of the internal state. So the embedded system itself is a physical device, and for a lot of its operation, an insight into its own physical state matters. Trivially speaking, temperature, for example, so that you can do thermal management. In case of a robot, it may be things like how fast the robot is moving, is it sort of, upright, if it's in the right orientation or not, those kind of things. So things about the system itself. So internal, external. The internal ones are called proprioceptive sensors, one's own. So and extroceptive sensors are sensors on the one outside. If you think of our sensory systems, it's the same way. We have external facing sensors, eyes and ear and things like that, but we also have internal sensors. Anyone? Like what? Hunger. Okay, hunger. Sense of balance, right? I mean, pain sensors, all those kind of things, right? So analogously, kind of they exist. Again, going back to kind of even ordinary embedded systems, so temperature is by far the most common one you would have, but there are other types of sensors also you might. Can anyone offer me examples? I'm not looking for robots. Just imagine like an electronic board. Okay. So besides temperature, what kind of other sensors do a system might have, which are internal?
The current sensor that senses if it's drawing too much power or whatever.
Right. So how much power am I consuming? And the reason we need that is because power consumption is in turn a function of the data I'm processing, the environmental condition, the amount of power the system consumes depends upon the ambient temperature and things like that, but it does so in rather complicated ways. So if I could sense how much power is being consumed, then you can adapt the performance to it. So this kind of introspection into the power consumption is useful because it's hard to model and predict otherwise. Okay, what else?
Some things have gyroscopes.
Yeah, why would they? They do have gyroscopes, but what are they trying to sense? Yeah,
Like angular velocity, I guess.
So why would I be interested in angular velocity of the system itself? But accelerometer is useful. Why?
in acceleration and which direction it's going.
Screen orientation. That's how actually. That's why the smartphones originally had accelerometer, right? Screen orientation. It will just orient it so correctly. Cameras have it so that you don't have to manually rotate the photo later, right? Even you might imagine some uses for gyroscope also, although often I can't think of one, or at least an obvious one, but accelerometer for sure. Yeah, pretty useful. What else? Any other examples?
Drones have a lot of an entire unit just for.
Drones are like the watch, so pretty much anything. Yeah, so they'll have full 9 degree of freedom, IMU to know their own state, right? Okay. So, and anything else? Inward facing, internal state. Proximity is about the external world, right? I mean, that's about one's relationship with the external world. Another very common one which electronics has begun to have are sensors which are detecting phenomena like aging. So electronics ages, when electronics age, and when it ages, it fails. So there are ways you can begin to measure that. So there are sensors which in effect kind of look at how slow the circuit has become, and then from that they infer aging and failure happening. So that's another example. That's kind of equivalent of, I don't know, like pain sensor, human body, something like that. So plenty of examples. External one is obviously far easier. In either case, what you get at the lowest level is some analog data, and then you have to make this inference about whatever you are of interest there, right? But in some cases, the inference you are seeking, the state that you're estimating, is almost one-to-one mapped by the sensor data. In essence, what I'm saying is the sensor data directly gives you the state of interest. In other cases, there may be a large gap. And it also depends upon what we call as a sensor, right? I mean, if you think of Fitbit, you can think of the whole Fitbit as a heart rate sensor, or one of the things that it senses. But it's truly not sensing heart rate. If you go deep down, it is measuring using PPG, pulse photoplethysmography. It is measuring some low-level analog signal. From that, it's doing some signal processing and some other algorithms to kind of derive the heart rate. Okay, or likewise, ECG can give the heart rate, but deep down it's just an electrical signal, and you measure the heart rate by looking at the periodicity. But it just so happens that that processing in many cases comes bundled with the sensor. So what we get out of the sensor is something which is pretty much what we get to be interested in. On the other hand, oftentimes there are things which are so far removed from what the sensor typically provides that you, as the user of that sensor data, have still sort of a lot of processing to do. Let's say I have a camera. Camera gives the image, and I'm trying to infer, let's say, number of people in the room. So big gap. Obviously, you have to do a lot of processing. The camera is not acting that way. And I think increasingly that's the situation we are in. That is, we get some sensor data and we seek to make an inference. Oftentimes, the inference may depend upon output of multiple sensors, so it's not even directly tied to one. So these terms like sensors and transducers and all are used a little bit sort of loosely, and you can almost think of that kind of, we think in terms of a hierarchy, which is we measure something and then in turn that's used to infer something even higher level and so on and so forth. Let's say I want to sense whether someone is stressed or not. So stress turns out to have a very specific sort of clinical meaning, and one of the ways stress is measured is using heart rate variability. And in fact, if any of you are into sort of tracking your fitness and all, you know HRV is kind of one of the parameters that is used. Now, heart rate variability in turn obviously comes from heart rate. So while you have heart rate sensors, but then when they are used to infer stress, they are sitting at a lower level in this inference hierarchy. So usually in any system, you have these tiers of inference making that will go on, and then maybe individual people's stress might be fused at the population level to kind of see, I don't know, things like does living near freeways cause more stress in people, things like that. So sort of each level corresponds to a different level of inference making. So sensing uh, is generally about state inference, and therefore important to keep in mind is that the sensor measurement, generally speaking, is not going to be the same as the state. But in some cases, that might be the case. So sensor will tell you value of some analog variable or digitized version of that variable, and then using that data, usually in combination with other sensors or over a period of time, you will have to then begin to make inference of interest. So for example, I want to measure distance, I may have a whole bunch of different ways I can approach that problem. So I guess one of the design challenges that you kind of face is that to do any given sensing task, you have to kind of go through this, what underlying sort of sensing modality is going to be the best one, and how do I go through this layers of algorithms. And in a later lecture, I'm going to sort of talk more about it, but some of the questions that you face in this process is things which are things like, how should I sample the sensor? Should I sample it periodically? Looking for some events. If I'm sampling it periodically, at what rate might I sample? So E, Nyquist rate, and all those kind of value stuff. Then how do I estimate the state of interest? In some cases, it could be very simple. It may even be as simple as thresholding the signal. On the other hand, lately, as we try to make more complicated inferences, we bring to bear a lot of machinery of machine learning and those kind of techniques to bring to bear. So there's a spectrum of techniques ranging from very simple signal processing to very elaborate machine learning kind of algorithms. And I think lately the latter has got a lot of attention. So things that I have listed out here, these are usually simple things. You might even imagine that sensors you can purchase already give you that, in the sense that they already have the necessary inference making built in. I want to know pressure. So you can literally buy something which gives out a calibrated pressure reading or acceleration, these kind of things, even though under the hood they are obviously converting some electrical signal into a acceleration reading. But on the other hand, let's say using images from a camera, if a drone wants to figure out where it is or how high it is or how rapidly it is moving, all of these things are going to require much more sophisticated algorithms. So when you think about sensors, some of the things that are going to matter is what's the data source that I already talked about, what's the signal form you are getting out of the sensor. In essence, it's some sort of typically it's going to be some sort of a time series of values. You may either be getting analog or sometimes it's just digitized within the sensor package. So ultimately, you're getting some sort of a waveform. Most importantly, the processing required. Oftentimes, the trade-off is you can use some general purpose sensor like a camera, but then at the cost of some enormous processing. On the other hand, maybe there's a simpler sensor that you could take something like intensity of light level in this room. I can use a light sensor, which is a single photodiode, and work on that. Or I can use a camera and kind of average across all the pixels and make some estimate about lighting. So different trade-offs, and it would depend upon what else your system is trying to do. And another aspect which distinguishes sensors is whether they are active or passive. So passive sensors do not emit any sort of energy, but rather they just observe the signals coming onto the sensor from the world. Okay, so they are purely relying on incident signals, whereas active sensors are the ones which emit some sort of physical energy, pressure waves or light or radio waves or whatnot, and then let that interact the surrounding world and then capture the return signal. And sometimes the same sensor can act in both modes. So I can have a camera just observing the world, or the camera can have a flash so that it can irradiate the world and then look how things look. But more, or likewise, I can have a radio receiver just looking for the radio signal versus it can transmit and then look back at the signal that comes back. So these are various dimensions. When it comes to analog signals, analog sensors, deep down, somehow some physical variable gets converted into either current or voltage or very commonly, and then you're, but it's also possible to affect some other property, but ultimately you're going to measure, that gets measured. A lot of the sensors are basically just voltage sources of some form, because they often arise from underlying electrochemical processes or underlying like physiological signals and stuff like that, and they're basically trying to measure those. But there are other types of sensors which are current sensors sources. Ultimately, some sort of technique you would use to convert it into A to D conversion, kind of something which is well hashed out in the circuits part of electrical engineering. So I'm not going to go over that. Fundamental for us, perhaps, is how do you sample the signals? So, or the sampling rate. So, I guess, if you're me in your graduate course, sorry, your undergrad classes, you would have been introduced to Nyquist criterion. And Nyquist criterion basically says that if I can sample a signal at least at twice the highest frequency in that component in that signal, so if you take a Fourier, draw the spectrum, take the highest frequency, if I sample it twice that, then I can perfectly reconstruct the signal without any aliasing kind of effects. Yeah. But so reconstruction is great because that means that the digitized waveform has everything that the analog waveform has. But it's pretty rare that that your goal is to reconstruct the signal. You are usually going to be making an inference from that, right? From that waveform. So if that's your goal, then it may not be necessary to sample in a manner which lets me reconstruct, because I can certainly reconstruct and then do whatever computation, but that intermediate step is not always necessary if what I'm trying to calculate is something simpler. So like, for example, let's say I have a waveform and I simply want to find out its DC value, its average value, right? I could certainly digitize and then take the average, or I could do what statisticians do, randomly sample and average them out. I do it at a sufficient rate to get good values. So there are a variety of different ways you can approach this problem. The reason it matters is because in many systems, the process of sampling takes a lot of energy. Rest of electronics, you can really depends upon the sampling rate. If your sampling rate is needlessly high, then the rest of your circuit is going to operate at a higher rate. Think another way also. We sample these signals, we digitize them, and then we usually are able to compress them. In fact, we are able to compress them even losslessly in many cases, which also goes on to suggest that our sampling process was sampling unnecessary stuff. So another direction in recent 10-12 years has been that can I sample in a manner so that I only sample the necessary information to reconstruct and not extra stuff. So let's think about it. Let's say I tell you that this thing is a sine wave, a signal that you're sampling. So at, let's say, 100 hertz. So Nyquist rate would say that I need to sample it at 200 hertz. But how many parameters the sine wave has? It has amplitude, it has frequency, and it has a phase. There's 3 parameters, right? So I just need to sample sufficient enough so that I can estimate those 3 parameters. And after that, any sampling I do is entirely superfluous. So if I knew kind of the underlying dimensionality of the signal, I can be smarter about the sampling.
But you can only do that if you're guaranteed that the signal is not changing.
Absolutely. If I'm guaranteed that So if I knew something about the signal characteristics, right? But I just want to point out that knowing something about the signal can help you devise a better sampling strategy. And likewise, knowing something about what you're going to compute from the signal can help you devise a better sampling strategy. So this whole area is called sub-Nyquist sampling, and you'll hear terms like compressive sampling and things like that. But the eventual goal is that basically we reduce the number of samples that we are capturing relative to the Nyquist rate. So Nyquist rate, anything above Nyquist rate, you probably should never be doing anyway, barring some beautiful margins. But what this shows is you can get away with a lot less in many cases. Again, provided you know you have some insight into it.
I think it's also worth noting that you can also sample it much higher than Nyquist for quality. So
true. And you can actually, there is a trade-off between number of bits at which you are sampling and the rate. So I can sample at a high rate and digitize my signals with fewer bits. So you'll hear for sampling there are two things which are matter: the rate and each sample, how many bits I am resolving it down to. So you will see these kind of samplers which are called which are sampling at very high rate. You'll hear these kind of terms like back when we used to buy CD players and DVD players and all, you would often see these things like it's a 1-bit A to D converter. What does that mean? Well, actually, what was happening there is they sample at far super Nyquist rate at a very low resolution, and then using some signal processing techniques, converting it back to a sufficient. So it turns out that if you have too many bits, then the analog circuits kind of have a different set of trade-offs. So you really kind of think of it like I have a bit rate budget, and I can use that at high sample rate, lower bit. So sampling resolution, the number of bits at which the A-to-D converter is sampling, and that in turn leads to a quantization error. And the number of bits you ought to be sampling at depends upon, in a sense, it's kind of like a noise, and therefore it will affect your downstream inferences that you are doing. Or in rare cases, there are examples where we do want reconstruction. Music is one example, right? Some analog waveform. After all this stuff that your CD players and all do, it's hitting our ears, and we kind of believe that we want to hear the entire waveform. Not entirely true, but let's say we do, in which case the sampling rate will be decided by the highest frequency we can hear, not anymore, because anything beyond that is being cut off anyway. And the bit resolution will be decided by how sensitive our ears are, right? I mean, there are, inside our ears are little sensors, and whatever is the tiniest voltage, they can be sensitive to. Anything beyond that is superfluous. So, but our ears are far more complicated. We are sensitive at some frequencies and less so at others. So you can make use of what our brain is doing with those signals again going back, right, as part of the sampling. But fundamentally, all A to D converters somehow have shown kind of a simple circuit where it's a pretty awful example of an A to D converter. But basically, it takes the input voltage and it compares it against a bunch of different thresholds. Okay, in this set of resistors are basically just generating different threshold voltages, and then using a bunch of comparators, I'm encoding it. That's not how, you would just burning energy through this set of resistors, so not a very good idea, but conceptually, I'm basically generating some n-bit number and doing this process repeatedly. Okay, and again, the entire courses are all dealing with that kind of stuff. For our purposes, again, it's a sampling rate issue and the trade-off against number of bits that should matter to you. Most processors you would find, they'll say, I have a 6-channel A to D converter. So what they really have is they have a single A to D converter and they multiplex. So they may have 6 analog pins, and using a multiplexer, they will connect one to the A to D converter and then move to the next one, and kind of round robin through that. And of course, a trade-off there is if I'm using only one pin and digitizing it, then I have the entire sampling rate available for that one channel. If I'm using 2, then it goes up by half, and so on and so forth. There are some other ways of organizing sampling also. So one pretty interesting trick that Professor Paul some years ago published in his papers called event-driven sampling. And kind of the idea is the following, that I put some analog circuit which somehow is able to monitor how much has the signal changed since the last time I sampled. And if it has changed sufficiently, only then I will sample. So kind of the idea is that the signal is basically relatively flat, I'll never sample again. Okay, so delta from the last sample. It sounds, the tricky part out here is how do you know what the delta has been because you are putting some additional analog circuits. But again, these are the kind of things that sort of people have been doing. Like I said, part of the reason is because the analog circuit itself and this A to D converter, these are often energy hogs, particularly in extremely low power systems where they can dominate digital processing. We know very well how to reduce the power of. In fact, in theory, I'm going to take sort of caveat to it, but in theory, we have very systematic techniques to drive down the power consumption of digital processing asymptotically to zero. But analog is a different beast, and therefore all these kind of things become important in systems where we are dominated by this edge of our system, right where it is interfacing with the physical world. This is an example of a light sensor. I'm going to skip through it. So sensor noise and errors, I mean, that's really what makes sensing challenge. So that sort of the signal that is being captured, as I already said, rarely would it be the case that you are sampling the state directly, right? You are the observation you are getting from the system and the state you want to infer, the state is latent, is hidden, and you have to do some inference making to get back the state. The problem is that the presence of noise and lack of calibration and these kind of things introduce uncertainty. So there are lots of issues, just measurement noise. All these measurement phenomena deep down suffer from various type of thermal noise and those kind of things. Sensors have limitations, like for example, they may have range beyond which they don't work properly. Okay, so anytime the signal strays out, you have a problem. And this the inversion function, like how you compute the state given the observation, may itself not be mathematically fully understood in the sense that you may not know the precise model for it, so you have to somehow learn all of this stuff. And by the way, the noise is not simply about sensors. You will also have noise in actuators in the sense that if you're taking action, your actuators have noise, like you may tell the motor to move 30 degrees, but it doesn't move 30 degrees, so no longer can you just say, oh, I asked the motor to move 30 degrees, and therefore I know the state of the world has changed by 30 degrees. That would be the case. There is uncertainty in action, and that in turn means that I am uncertainty about the state. So, point is that what we're really doing out here is we're trying to estimate the state under a scenario where you have tremendous uncertainty because of all these kind of factors which sort of come in. So some of these things are noises and errors and all you can seek to remove right after either at the analog stage or right after you have digitized, and they usually go under the umbrella of signal conditioning. And kind of the idea is that these are things which we perhaps understand well and how to remove or compensate for. So, for example, if my sensor is noisy, maybe I can filter away the noise if the noise is reasonably well behaved. Can apply some sort of a Gaussian smoothing or things like that to kind of do it. Other examples, so like for example, if I have a switch whose state I'm trying to sense, a very common problem is that these are mechanical devices, so when you turn them on or off, instead of just cleanly changing the state, they kind of vibrate a little bit. And therefore, when you are sampling it, your actual signal might look something like this. That is, at the transition point, there might be multiple ups and downs. And so if you were to, let's say, design a system which is simply triggered by the edge, it might trigger unnecessarily, right? It might count incorrectly how many times it switch was on and off. So you'll have to smooth this thing away. You want to kind of suppress this part of the signal into kind of a single smooth ongoing edge. So again, it's a smoothing or a filter out the noise. So usually these kind of obvious things you kind of do just upfront, often on the analog side, and sometimes the very early stages of digital filtering. You don't want kind of to complicate your downstream inference making. So averaging is a very common approach. You kind of do a weighted average over a window. Another very common thing you do is take median. So do median filtering. So the idea is that sometimes your values are so out of whack because of some weirdo things. So taking an average is still not sufficient. So you kind of do a median filtering. For these kind of things, there are techniques specifically designed for these switches and all, but the underlying concept is the same. You're basically filtering things away. So early stage of sensor processing is the signal conditioning. You'll almost always do it. It will probably already be done as part of the sensor package. But even then, there is a lot of noise. If you just capture data from accelerometer in your phones, you would see how noisy it is. Okay, there is some distinct trend in there, but it's just these things tend to be swamped by the noise that you see. Another challenge that one has to deal with is the calibration of sensor. And kind of the main thing out here is that let's say I want to give a physical interpretation to what the sensor is outputting. Okay, but remember, under the hood, it is still measuring some electrical signals and all, right? And that mapping from that electrical signal to the unit in which I want to represent the physical quantity, that mapping may be unknown, may be affected by characteristics of that sensor. So I may have to go through a calibration phase. And almost always if you take n copies of the same sensor as a manufactured, same part number and all, they'll behave slightly differently. So you have to calibrate. And moreover, that mapping from the underlying physical, underlying voltage that you're getting or reading that you're getting to the physical quantity of interest often varies. It's a function of time. It often is affected by aging. So you may have to have a continual process of doing this calibration. So essentially the problem of calibration is really finding the parameters of the model which relate the underlying voltage or current that you're measuring and the physical quantity that the sensor is supposed to be measuring, and kind of bring that. There are a few distinct ways you can kind of approach this calibration process. One is I can compare it against what is called as a gold standard sensor. That is, I have some high quality reference grade sensor, and given the same input, I expect my sensor, that reference sensor, to have the same output. You make multiple readings, you hypothesize usually some simple low order polynomial type calibration curve, and you learn estimates. Another possibility is that you don't have a reference sensor, but you have a reference input. So if I'm measuring, let's say, salinity in water, I can create solutions at different measured salinity levels and see what my sensor is reporting, and again kind of calibrate. This process of calibration is painful because it takes time. So If you buy calibrated sensors, then they cost more because at the factory they have to do it one at a time. On the other hand, if you are doing it at runtime, then you have to find a way of doing it, doing this process. Um, uh, a lot of our devices need calibration, even things like crystal oscillators in electronics. They vary from device to device to device. So if you really want to calibrate the frequency with which your computer is running, you have to either buy a precision type of precise oscillator, like a rubidium clock or something like that, or alternatively, you have to calibrate it against some reference source, and that is what things like time servers, NTP, or to kind of engage in a sort of repeated handshake messages with it to gradually calibrate your clock. So clock is easy. I can go over the network and kind of measure things, but a lot of other sensors are hard. Let's say, for example, color calibration of a light sensor. You would either want to buy something which is reference grade, or you would want to then have a mechanism like calibration sheets and calibrated lighting conditions, and then kind of do it. So it's not something to be ignored, because if you ignore it, you basically are going to get bogus results as an output, because anytime you're attaching a physical meaning at some point, then that would be off. But interestingly, in many control systems and all, where you have a feedback loop, maybe the calibration won't matter, because the act of feedback loop is going to suppress that, right? I mean, even if I don't learn the parameters, because I'm always correcting it, things I can suppress that. So in some cases you can get away without calibration, but generally not. So in many of your projects you have a sensing element, so you should make sure that your sensors are producing data which correspond to the physical reality that you are talking to. Another aspect of sensors that matter a lot is fusing multiple sensing modalities. And there are two reasons you might have sensor fusion. One is that my given sensor is noisy, but under certain kind of noise distributions, if I have n copies of the same sensor and I take the average, I can do better. So, for example, if noise is Gaussian, then you can get away with that. But there are other reasons why I may have multiple. I can combine. I may have to combine readings from multiple sensors. So this slide kind of largely talks about kind of noise and therefore the resulting accuracy. But other reasons include that no one sensor may have sufficient information for me to infer the state of interest, but multiple of them have. Or they are giving additional information. So like, for example, when I try to localize an object around me, rely on my eyes, but I also rely on my ears, the sound it's making, right? I mean, so like the car coming by the road, because they are all providing kind of complementary information and complementary failure modes. So it's very common for systems to sort of take these different pieces of information. Also, sensors may have a different view of the world. So I may have two cameras, but they're looking at different segments of the road, and by combining the two, I may get a more meaningful estimate of my state. So fusing sensors, sensor information is systems of sufficient richness that's almost always present, and you may be doing it as part of some simpler signal processing algorithm, or it may be part of some things that we would refer to as machine learning kind of things. But at some level, it's always visible. So. So basically, to summarize, then these issues. So conditioning, which is basically handled pretty much close to the within the sensor package, calibration, which you will often have to do, and then finally fusion to benefit from the diversity that different multiple sensors and multiple sensor modalities that might provide to us. One of the challenge, again, that you're facing in the choice that you make for a sensor is how much processing you have to do it, in the sense that if you pick a sensor which is closer to the state of interest, then you have to do less processing. On the other hand, it may be that I may then need many specialized sensors. On the other hand, um, there are sensing modalities like cameras, which are very close to being universal sensors. I can sense a lot of different things from them, but then I have to pay for that by a lot of processing that I have to do on it. So I think as these autonomous vehicles and all are emerging, I mean, that's you see some of that playing out. Like Elon Musk has made the statement that cars can be fully autonomous just based upon cameras alone. And this statement is basically based on the fact that we humans, largely when we drive, are relying only on our eyes. The only thing is, I guess, there's a gap between what the artificial vision systems are capable of and what we are capable of, and therefore other sensing modalities have a role to play. The second thing is we fail as drivers, and therefore other sensing modalities maybe can result in a safer system. So you see this debate playing out now. I think back in last year, that accident where kind of a Tesla drove under a big rig which was kind of stranding the road led to that limits of at least the vision system as it was, namely apparently it confused it with a road sign, like those highway signs and all. So after that, it's a radar first strategy that they adopted in the car. So that was a big change that happened. But the thing is, I guess the right combination of sensors which work robustly across a lot of conditions and all is pretty tricky to have. Okay, I was reading that kangaroos jumping across the road in Australia fool these autonomous vehicle systems very easily. I didn't fully understand why. All these kind of presence of fog and stuff like that. So complementary sensing modalities have a kind of an important role to play. If you can afford good, expensive, costly sensors like LiDARs and all, which are as expensive and often far more than your car itself, then you get a lot more robustness. For more low-end systems, the kind you're going to encounter, usually we have kind of a lot of simpler sensors for special purposes, and then we may have a general purpose sensor. So like, for example, your phone still has a light sensor because it uses it for proximity, even though you could argue that camera can give the same information to it, but then camera requires a lot more processing and would be very energy hungry. So you would, much like we saw big dot little for processors, you can think of a similar big dot little for sensors, namely some simple specialized sensors and then kind of more universal rich sensors kind of together working towards some common goal. The sense, this is a point I made very early on, that in some cases we seek to sense because we are reconstructing the world in some manner. Okay, it could be for purposes of having data that can be reused later on. So literally, I may just be taking images and all, and that can help me reconstruct all sort of attributes of the world. But more typically, you have these systems because you are making some decision based upon that. So at one end, I have um, the low-level sensor readings, and then on the other end, I want to make a decision like how to to turn the steering on the car. If that's the goal, then I don't really need to go through reconstruction of the signal as I mentioned earlier. And in fact, I'm really interested in just the decision being correct. I don't even care about if there is any semantic, human understandable semantic attached to any signal in the middle, right? So I have sensor data and I have an output, and I don't really care what's happening in the middle. And a lot of systems fall into this category. Now, simple sensors can be used for that. Switch indicates a robot has hit something, and a bumper switches on the robot. I can just back off or stop the robot. Okay, so that mapping from sensor to action is can be done very easily. But I can't really know about this as a reconstruction of the world. On the other hand, imagers and all are much richer. So they can be used for both kind of documenting the world so that we can reconstruct it, as well as for this action taking. But when it comes to action taking, or there are kind of historically the approach with these kind of complex sensors as vision and all have been that we do it in a two-part thing. First, we take the images and we make an inference which, in terms of which we know how to make the decision. So like for example, let's say I'm designing an autonomous vehicle, it has a camera in the front, and I want to control the vehicle so that it stays in the middle of the road. So how would you approach this? So camera, front facing, let's say the road has lines, you want to drive in the middle.
Keep an equal distance between each side of the road that you see.
Okay, and to do that, you will first need to figure out from the name
Transition of road to not road.
road to not road, so road to line. So you're going to do the line detection, right? You know something about your speed, right? So, but we are decomposing it into an intermediate step where something which we as human decision makers understand, namely road lines and all, and then something about geometry and kind of keep things in the middle, right? And that's a pretty reasonable, natural way of kind of doing things, that we take that raw signal and we, step one, we kind of map it to some sort of a symbolic representation, if you may, that we as humans understand and can articulate a decision rule in terms of, and then we take that and define our decision rule, as you were saying, keep equidistant from the two. But when you think about it, we don't necessarily have to do that way. Maybe I can just map things from that complex image to a driving steering control decision. And some of the work lately, I think I sent down, I guess, to you the papers. Those of you who are doing autonomous vehicle work, you'd see that some of the work which has begun to emerge is kind of taking that approach. It just takes images, feeds it into a neural network, which they have trained, and the output is the steering control. Nothing in the middle. There is somewhere deep inside, maybe the neural network is learning the concept of lines and keeping equidistant from it, or perhaps not. Maybe it has figured out some other strategy. So for complex sensors, now we have this other way which has begun to emerge, which is just bypass this intermediate step. You kind of do the end-to-end sensor to action, sensor to decision as a one opaque step, not sort of make these intermediate inference making. You can think of like medical decision making, stuff like that can also fall into the same category. Currently, we take all these things and then we attach sort of meaning to it, or the doctors do, in terms of what they are taught in medicine. But you could also imagine kind of a future where a whole bunch of parameters of human body are taken, and the outcome in one go is intervention or treatment, and we don't try to attach any meaning to it, like, oh, your heart is failing, or your kidneys are failing, or stuff like that. None of those things. Just kind of do a kind of a holistic kind of thing. So something analogous has with machine learning and all that's going to happen. There's a problem though, which this leaves kind of a sense of dissatisfaction that we don't understand what these things are doing, right? When things fail, you would like to know in human understandable terms what happened. And So one of the things which has emerged in this thing is, can we make these systems interpretable or explainable? That is, they can rationalize why they took that decision, and that may very well mean that they may have to then go back to, in terms of lines and objects on the road. So it might say, I veered to the left because there was a pothole there, or things like that. And doing that kind of explanation might be important in some sense. So, but right now we are kind of in early stages of this kind of end-to-end approach to sensor processing. That's going on. Okay. So you can think of some complicated task and then try to sort of see how would you approach uh, doing it all the way from sensors that you will use to the inferencing techniques that you are going to use, and so on and so forth. So let's say I want to know how many people are in this room. There are many different ways you could potentially approach this thing. Suggest me some.
Well, there's software out there that has face recognition, so you just use face recognition to.
Okay, so I can have a camera up there, it's taking a wide angle view, and there are face recognition software, so I can count the number of faces and get approach that way. Okay, so that's fun.
Check the Wi-Fi boundaries.
Check.
How many connections are
Okay, if you could, but sure.
Find change. So based on the image of the empty room,
Mm-hmm.
see about how many bodies have entered the, or seats in the room.
Okay. Okay. Yeah.
Thermal camera.
Thermal cameras. Okay, so that's another type of imaging. Absolutely, and might be easier to do 100%.
Maybe a sensor on the door.
Maybe a sensor on a door, right? So I can, if a sensor can give me transitions there, I can, and knowing that at some point the room was empty, I can kind of, well, keep a continual count of that.
And the pressure sensor on the seat.
Okay, sensors on the seats. So absolutely, and hopefully these examples are leading to, all of these choices have different trade-offs in terms of how hard it would be for us to make that inference, the deployment cost, how easily they could be fooled or not fooled, and all. And I think um, for anything reasonable that you would seek to infer for a decision making, you would see that these choices you end up facing. I guess I'll go back to saying camera currently is kind of close to being a universal sensor that I can sense a whole lot of stuff just with a camera, but not necessarily very easily or accurately, given the things that we as humans can, but for a machine to do it, the algorithms may not be quite there. But in many cases, they have become better. So, one of the standard sort of competitions which takes place for labeling images. So it used to be that humans were significantly better than the classical techniques, which were based upon identifying features and then based upon those classifying things. Then when deep neural networks came, it was a big improvement. And then within 2-3 years, they beat humans. And in many other domains like transcription of speech and examples like that, the same thing has happened, that computers can beat humans. On the other hand, there are so many other things that they are just awful at. So time would tell what kind of certain things which is always perhaps would be pretty hard. So when you are selecting the sensor, then you have to you have to make sure that you sort of take into account the specifics of your application in an engineered setting. So there are sort of two different kinds of goals that motivate people. There are some people who are motivated by that I want to create a human-like entity, okay, which can live in this a human-like entity with similar power, and I want to do the things the human way. Okay, so their goal is to beat human vision systems and human acoustic sensing and stuff like that. And then the other one is a narrower task-specific viewpoint. I'm designing an autonomous vehicle. I don't care what suite of sensors I use. If it can drive safely on the roads, I have my job done. And both are fine. One is more, I guess you could say, driven by a particular intellectual crusade, and the other one is more of a pragmatic. So this is another one, measuring distance to an object. Again, there are zillions of ways you can imagine doing it, all have various kind of trade-offs and all. And so anyway, I've kind of listed some of them. So sensing, I'll have a longer lecture going over some of the processing techniques and all, but sensing is this is probably at the heart of what embedded systems are about, because an embedded system without sensors is probably not going to be doing anything tremendously useful. Okay, so let's take a short break, and then I'll move to the next topic, actuation, and then.
I can think of one system like I think it's called smart water, like watering something where all they do is they respond. Yeah.
Yeah. So I guess the only examples are where I'm only doing an action according to something.
Pretty much, yeah.
Right? Clicking knives for pleasure. Right? Making random sound to keep away. Stuff like that, right? I mean, so absolutely. But spotting, I mean, actuation without restricted actuation. Okay. Actually, so yeah. So how many of you are there? Yeah, only two. Yeah, so you can do a computing system, or you can either one of you have iOS expertise. iOS programming. Yeah. Yeah. Who was the student who contacted me about the seminar? Yeah. You're mail on Piazza, right? Mm-hmm. Yeah. Okay. These two guys also want to do it, and so maybe you can okay. Okay.
Question what's an ADC? What's on the microcontroller? So usually encounter project situations or have things, but only have one ADC. So then, yeah, also they choose a rotation. So
you can program that in many different ways. One is you can just do a programmatic sample collection. That's what I don't really want to do.
So if it's rotating, we'll separate
it will be 1/3 of the peak, right? So if I have a single channel, let's say for one channel, 100 Hz, two channels.
So it's already programmed.
Actually, your limit just like that.
Oh yeah.
Yeah. So it may be that allows you non-location
so he or gave us like the
more commonly
So what's the one? You're doing the secure network talking so we kind of decide which kind of Linux.
So can we do like
you have any recommendation?
so within my lab, I guess we have most
easy as possible, like easy to interact and easy to
You could also use
we don't want to do too much like
order those these small Intel Intel nuts, the tiny little boxes. That I guess the advantage there is Intel platforms are so that's the positive. We are kind of sustainable and embedded.
Yeah.
I had talked regarding activity recognition. So first, like, he is ready to like give data from our screen, and I was told that you are also ready to give
Which activity was it?
activity recognition using Wi-Fi chips.
Using Wi-Fi. So I think we need to talk because do you know how to work with sales times? I think we must set
A bit like I do have good experience with smart, not too much.
because the thing out here is the model out here is that I'm scooping in someone else's home. So it's not the Wi-Fi packet as my access point, but the Wi-Fi point equal. So you have to essentially log all sort of traffic. Another thing I would say is probably I think you'll get a lot more interesting data if you not simply limited to Wi-Fi, but also look at any other traffic which exists by way of radio. So usually at home you have several different things that are all operating in either Wi-Fi obviously, with activity, you have VLAN activity, and you have Zigbee. If there is somehow one port would be active, you get 4 different radios, and then you message them, you will get a lot more insight into it. So one way you could do this thing is that set up a Linux box where you have Wi-Fi, V-Wave, USB, and you put them into a promiscuous mode or log or the first thing you do is collect and then do some sort of clustering in order to see that you have to select so that would be kind of my solution there. And another issue is I'm talking about is in a small apartment after a place. So you will find but not in your home, unlikely you will have coverage for most things. So you don't want to have multiple of these. Thing to make sure is that you are the packet contents are going to be so you have to manage so yeah, I'm fine. So what I would suggest is first order my business, some small platform I didn't have a chance to all the things that I'm talking about.
Yeah,
it's used by all these smart lighting, which I do have at home. I also have for another one which exists in homes as security systems, and these operate in land with
how is it supposed to work? Like, how is it setting up stuff?
Yeah, you give me a box, and so the idea is just give me a box.
When they're basically should be doing
So, Wi-Fi, drive, leaving, and this is a big and then you essentially have
don't get back until one day down in the bottom camp, and then so actually it ended up being a lot worse because when I pointed out my car was going to drive another person with me. But another problem is like whenever I didn't do any work, so you mentioned like few things where I can like so initially I think I was kind of supposed to take one final check of my car, like more into literally water down. I wanted to like you know like what should be our manual, like how deep should we go? No, I think I would say car I think it's an hour and a half by taking so so I'm more likely to all the way from I started all yeah, there are several but more than and we get there for all of us. That's latest by we got there. Doesn't have we're like, okay, so we have like 3 hours or 4 hours to sleep. So just kind of what's it? I think you can. I mean, I think it's so yeah, I think it's one of the ones that pain and you want. So I have a 7.5 hour drive where to sleep. So you don't have this why of something. When I came back like on Monday, I like paid more like 7,000 pounds. So now you modify the model. 6,000 before that, it's all about just frames holding on to the inverter itself. How many different time and so yeah,
Is there one version of this resource like machine learning style things? And there's some also smart learning notification.
Makes sense. Yeah, but it's not just trying to learn.
Okay. Something else.
And then I'm meeting so what about later? From 5:15 to 5:45. From 5:45 to 6:15. Okay, let's start. So, so Leon here pointed out that there is a reasonably useful category of embedded systems without sensors, and these are systems which just do a pre-scripted sequence of actions, like for example turning on sprinklers at one's home. Every time, I guess the only thing they're sensing is time, but other than that, they basically just go on a repetitive cycle. And I guess these kind of things are also present in other settings also, where they kind of just do some sort of a scheduled action.
Is it really sensing time, or is something else just sending a signal? Yeah, I think you can make it even dumber than that. You just scream a signal like an EM.
Okay, fair enough.
All they do is they just respond to that.
No. If you scream something, then they are sensing.
Yeah.
Right? So, yeah. So I guess the sensing of the time part is, I always view oscillators as something which sense time. But you could argue that they don't. They are not. Okay. So. Okay, so there is at least that class of systems. Okay, let's move on to actuation. So many embedded systems. Well, firstly, almost all systems, I would argue, involve action. The only issue is action at what time scale. In some cases, we collect sensor data, we feed it to policymakers. We make inferences, we feed it to policymakers, and then they institute laws and all, and that is the action that takes place, and that affects the world or the society or whatnot. But that's usually we will not think of them as actuation. I think here what we are referring to is something on a reasonably immediate time scale. After we have estimated the state, we are going to take some action to influence that state. It could be that the processor is heating up, so I'm going to slow down, or it could be that I'm measuring what target is there, and based upon that take some evasive action and things like that. So a terminology which sort of particularly used in robotics literature. So there's a action requires kind of two types of things. An effector, which is really the mechanical or physical thing which directly comes in contact with the physical world, so to say, and causes a change to be had, right? So it could be the hands of a robot, for example, or it could be the laser beam, which is bringing down an incoming missile. Okay, so those kind of things. And of course, as you might imagine, the choice of effector obviously depends very much on the task at hand. Actuator, on the other hand, is the mechanism which causes the effector to undertake a task. So it would be the actual motors or nano wire based muscles or things like that. So the analogy is hand is an effector and the muscles controlling the hand or the tendons controlling the hand are the actuator. And again, actuator also needs to be selected to provide the right torque and stuff like that and all. So when it comes to embedded systems that you commonly encounter, and this is kind of more the domain of mechanical engineering, although there is a fair bit of EE and materials type work which also takes place here. So electric motors, and lots of advances have happened there because being able to provide good torque with small lightweight motors is quite important, and particularly in things like humanoid robots and stuff like that, that becomes important because you don't want like a heavy bulky kind of a thing. Hydraulics is another one, pneumatics, air pressure based, and then other type of material which are affected by light incident on them and temperature effects and chemical effects and things like that which exist. So there are plenty of examples that of different kind of actuation modalities that exist, and but again, motors are the one which we normally think of in a lot of these motors, a lot of these systems, and sort of at least in typical lab settings and all, that's what you would likely encounter more. They are usually rotary, but you also have linear motors, which kind of cause linear motion as opposed to rotation. And mostly they are based upon electromagnetic phenomenon, but there are others as well. Very broadly, you have a few common type of motors. You have AC motors, which are basically, as the name implies, take alternating current. You have DC motors, which take direct current, and they come in a few varieties, and brushless, which have to do with the internals of the motor, and stepper motor, which kind of move in quantized chunks. And then you would also hear this term called servo motors. Anyone knows what servo motors stand for? Of course, it's just a standard motor. No one? So servoing refers to the fact that the motor itself has a control loop inside it, and it seeks to achieve certain particular physical variable that you are going to control, one of two, position or speed. So you'll find servo motors which try to achieve a certain speed, and you also find servo motors which try to achieve a certain position of the axis on the 360 degree scale. So these are motors where already inside the motors, as opposed to you simply getting kind of voltage which is being applied across the which is controlling the magnetic field directly. The interfaces to these servo motors are oftentimes some sort of a digital command basically, and then you're conveying to it, I want this speed or I want this position. Main thing is they're very convenient to use. So the way like in drones and stuff like that, what you would see is there are motors, and then there are usually kind of these little boards which you would have called ESCs, electronic speed controllers, and that whole package basically acts as the servo unit, and then those ESCs also take a lot of current because they have to supply the needed energy for supplying the torque basically which is needed out there. So as far as your embedded board is concerned, it basically is going to be sending some sort of a command which is indicating the desired speed or the desired position. Okay, you don't have to run that fast control loop on the processor to manage that the speed remains what you want or the position is what you want, but you rather are just communicating a digital value indicating the speed or indicating the position. Now, one of the things that comes up in this setting is that you don't want, like, let's say I want to send the speed, and speed is a multi-bit number. So one approach would be to have some sort of a complicated parallel or serial bus running to the motor, and then having a processor on the motor side decoding it and stuff like that. So maybe you can use I2C or something like that. You'll send it to the speed controller, and then that will take that and translate into voltage with appropriate current capacity. But that gets rather cumbersome. So much more common is to use a very simple way of communicating real values over just a ground line and one line, and that's pulse width modulation, which is what the very first homework that you did is about, right? So by controlling the pulse width ratio, I'm effectively communicating to the other side a real number value. And that real number value could indicate anything, could indicate, in case of command being sent to the motor, the speed I want or the voltage I want. And likewise, some of these motors have sensors to sense speed, current speed, and current position. And when they send back the data, they can send it the same way. They can send it as a pulse width modulated waveform. There are other ways here also. There are also pulse position modulation. So I'll have a frame and a pulse occurs somewhere in the frame, and the position at which it occurs indicates the real number value. Okay, so I can think of my frame as having of being at 100 slots, and slot 0 through 99 correspond to real numbers 0 through 99. I could also do pulse rate modulation. So the rate at which I'm sending the pulses indicate a real number value. So these are cheap ways of communicating real number values over an otherwise sort of one wire signal. And the reason it is done is because classically on the motor side, you couldn't really afford a whole lot of electronics, so you wanted something super simple. So PWM and all kind of grew out of that. You could imagine now that with electronics having been miniaturized significantly, as well as threats of security, that is, you don't want an adversary to attack your system by intercepting these unprotected analog commands which are going to the motor. Maybe the time would be there where motors have crypto processors inside them. They are paired to your device, and then there is a proper serial bus over it. So it's, I think, mostly because of the simplicity of these actuators that we have kind of stayed away from anything more complicated. Remember, it's not the issue of number of wires. We know very well how to communicate over a single wire with full-blown digital communication. But PWM was just so super simple that it's been around for us forever, and it's PPM, so pulse position modulation and pulse rate modulation, they are very rare. So PWM is what you would find most commonly, and most microcontrollers provide built-in support for it, because so that again your software is not burdened with generating it or even understanding it. Okay, I mean, you want to convert an incoming PWM waveform into a corresponding real number, you don't want to worry about kind of programming the control timers, timer counters and stuff like that. So usually it's just provided as a built-in peripheral for the simplicity that kind of comes with that. When it comes to motors, it's a relationship between torque, speed, current, voltage, and basically fundamentally the speed of the motor to the first order depends upon the voltage that you apply, and but different kind of motors are going to have different kind of a torque versus speed curve. DC motors are actually excellent at providing a very high torque at low speeds, which is why electric vehicles have this very rapid acceleration, because unlike gasoline engines where the torque reaches peak value after the engine at only at high RPMs, with DC motors you have sort of big torque right at the beginning. There are also other interesting ways in which you could use these things. So one thing again, if you recall from your high school physics and all, when the motor moves through the magnetic field, the rotor of the motor moves through the magnetic field, there is a reverse voltage which is induced, and that's called the back EMF, which essentially acts as a load. So essentially the voltage you are supplying, it is being dropped across the back EMF, which is being put by the mechanical load. So that exists, and as you try to speed the motor up more, that back EMF increases and essentially increases the load. Okay, you see it as electrical load that you are driving, and then as a result of that, the current you are going to supply decreases, and the torque therefore decreases, because torque is related to the current. So this thing kind of plays out in the electric motor world. One of the things is, by measuring the back EMF, you can actually sense the speed of the motor without actually having a speed sensor. Not very accurate, but you actually can essentially get a first order measure of the speed of the motor. So now remember, your microcontrollers cannot supply a whole lot of current. So the current which is needed to provide the torque is not going to come out of the pin of your microcontroller. Okay, so somewhere that current amplification has to take place, so to say, right? I mean, somewhere there has to be a high energy source which is actually supplying the current. So a very common circuit which is used, and this is which is built into the speed controllers which are part of the motors or which are next to the motor, are the so-called bridge structure. And kind of the idea is that the signal you are sending from the processor is controlling these switches. It's not directly controlling the motor. And this thing itself is being driven by some high power voltage source. And kind of the idea is that the speed with which I want to control the motor, I'm going to do it by supplying by rapid. So let's say I turn the left switch S1 and S4 on. So then the motor, the current will flow from top left to bottom right, and the motor will move one way. And if the switches are permanently closed, they will keep moving. And if I rapidly switch them, then the ratio would affect the speed. And as you can imagine, that's a pulse width modulated signal. So the PWM coming out of a microcontroller really go and directly connect to these switches. And by controlling the PWM duty cycle, you are basically saying what fraction of the maximum speed.
So you're constantly flipping the switches?
Yeah. These are transistors. So these are not switches in the sense of mechanical switches. These are transistors acting as switches. So you're rapidly at some very high rate, like 10
So
kilohertz.
the motor is going.
No, motor is not going back. Motor is getting current for a while and not. Getting current for a while and not. Okay, so that's what's happening.
Okay.
Supply current for, and then since motor itself acts as a low pass filter, so it smooths the signal away, and the DC component is really the pulse width modulated signals ratio.
So you configure in your microcontroller to only select S1 and S4 for a given.
Well, that's the wiring, okay?
Yeah.
So from your microcontroller, usually you will have two signals going out. One is one of two ways. So just imagine that I have one signal going out same direction and the other signal going out same speed. And depending upon what the direction is saying, I'm going to send the speed signal either to S1 and S4 or to S2 and S3. Okay, that way I can control the direction, I can control the speed. And now you can see why PWM became popular, because this thing is tailor-made for PWM. So that's where it's come from. So your electronic speed controllers, what they're really doing is they're taking, I mean, they have some protection stuff and all, but ignore that. What they're doing is they're taking your speed signal from the microcontroller, the PWM, supplying them to these switches, and they're taking sort of voltage from some high power source and supplying it out there. That's all they are doing. Conceptually very simple, but then they have protection and mechanism built in so that the motor is jammed and you have overcurrent protection and stuff like that. But conceptually very simple. So that's the genesis of PWM, and very common in both directions, to send speed information or position control information to the servos, and likewise getting sensed information back. And the best way of thinking about them is that they are essentially a way of communicating real number values on a single wire. Okay, so that's actuators. Okay, so we have still a few minutes. So software development cycle. So through this homework, you have already been exposed a little bit to that. The normal embedded system development cycle looks something like the following. So unlike our regular computers where you write code and you just run it on the computer, you wrote the code, here you are doing what is called as cross development. Okay, you write code on one type of machine and you generate binary and executable code, and then you run it on a processor which is inside your embedded system. So you go through this kind of cross compilation tool chain, and then you test and you kind of repeat. A very common thing which has emerged now also is the ability to simulate even relatively complicated devices. So if you're developing for, let's say, iOS or Android, these kind of things, these tool chains come with device simulation thing. So I can run that code where I have Android or iOS booting up on a simulated device, and I kind of go on the way through. And it's not just for these mobile devices. There are also packages which exist for common embedded processor, and actually I just got donation from a company called Wind River, which has probably the best simulator of this type called Simix. I'm still struggling to install it, but if I get it up and running, I'm hoping that in one of the homeworks you can kind of get exposed to it. But the idea is that if you're making a complicated system where you have processor and peripherals and stuff like that, you don't want to just charge ahead and kind of work with that test real hardware, because maybe the hardware may need to be redefined, particularly if it's a single chip kind of thing. So with Simix, you can construct a system where you have a processor, you have peripherals and all, and boot up your OS on it and run your applications on it, all within the simulation domain. Essentially, you can construct a model of your device which is at the level of a processor running things in a cycle-accurate fashion. Android simulator, at least for the longest while, used this very nice open source processor emulation platform called QEMU. So QEMU is, unlike your virtual machines, QEMU is a cycle-accurate processor simulator. Okay, and so it can really, then you can kind of take a QEMU thing and attach various kind of peripherals to it and all, and kind of really mimic a platform at a pretty low level. It's slow, but it works. I think in time since, sort of Android services will also move to other approaches, but QEMU works on all the platforms. So if you want to create, and it has support for like all sort of ARM processors and MIPS and stuff like that. So you can take QEMU, model a processor, attach devices to different places in the address space, and kind of model your embedded system and do the simulation. And then once you're ready, you kind of go through kind of the whole exercise. So there are lots of different languages, obviously, just like in the general purpose programming. There are lots of them which are available in this domain also. It used to be that programming embedded system meant sort of low-level system programming languages like assembly, C, C++, those kind of things. But lately, with things like Raspberry Pi and all being essentially Linux computers, a lot of what passes as embedded system programming is nothing other than using Python or some other scripting language with appropriate libraries so that you can talk to hardware. So like PySerial is a module in Python which lets you talk to serial code. So obviously, as you can imagine, very useful. Likewise, there are packages which let you talk to the pins so that you can toggle pins and all. So there are people have created these things, these packages, so that you can interact with things and kind of write, let's say, not real-time type timing constraint, but you can write reasonable things that you can interact with the physical world, particularly in sort of grabbing an image from a camera, reading stuff from a microphone, and the reason it has caught on is that much of machine learning stuff at present is on Python. So if you are doing any of this complicated sensor inferencing and all, probably your best bet is running Python, although there are also some decent packages for Java and C++ as well.
There are microcontrollers that can run Python.
Embedded platforms that can run Python. Okay? But by the way, there are microcontrollers which can run a language called Lua, which is kind of like Python, less popular, came out of Brazil. It's much lighter weight. So there are microcontroller instantiations of Lua. Okay. Let's see. Another thing which has happened in recent times, and again, I'm hoping that through one of the student presentations we can go over that when it comes to systems programming as in low-end stuff, or there are languages which have emerged which seek to provide safety guarantees. And a new language which has gotten a lot of attention lately is a language called Rust. And Rust has the property that you can, at compile time, verify that your program would not have certain kind of bad behaviors. I don't know if any of you attended like the talk from the UC Irvine speaker last Monday in the ECE seminar, and he was talking about how various kind of software errors and all lead to security issues. There are obviously besides security, there are also safety issues and all. So languages like Rust are kind of targeting that can be avoided through appropriate compile time analysis from bad things happening. Now, having said that, there is only so much you can detect at compile time, so runtime protections are always going to be part and parcel. The problem is microcontrollers are way too simple at the low end to have those runtime protections. So like, for example, your normal processor have a kernel mode and a user space mode. Microcontrollers, everything runs typically on a single address space, so they can just comfortably track each other. So lots of stuff happening in this domain lately. New system languages have also emerged. So you have Go from Google and Swift from Apple, which are more modern system programming languages, but they're operating in the same space as C, C++. Rust I mentioned as something which is sort of get into the same categories. So I think interestingly, there's development on both sides. That is at the low-level language level, as well as the emergence of scripting. The number of Python packages that exist for robotics and drones and these kind of things is just mind-boggling because it's just so easy to do it. And in a sense, what happens is where you could have used a microcontroller, maybe now you're using a Raspberry Pi, I mean, considering that the current iPhones are more powerful than many of the Apple's current laptops, that horsepower we can pack into embedded systems is quite amazing. And so we are seeing that one of the ways people are taking advantages of that is to make it easier to program these devices. So the emergence of Python and all is kind of indicating that. Okay, so I'm going to stop here. And so in terms of right after the class, after I have had my late lunch, I have to meet the ECE speaker. So I hope to be in my office available from 5:15 onwards. I know I have, so Shravan's coming at 5:15. I agreed with one other group for half an hour later, 5:45 or so. Oh no, that's 6:15. Did I say 5:45? Okay, you guys can come and wait, and when the queue is empty, I'll list. So.
Yeah.